This is section 10.3 of our limits unit. So this is all about one-sided limits, and it's going to lead us to a discussion, kind of a formal discussion of continuity. So look at my graph. It says the limit as x approaches 0 of this function. Well, I can look at this function from what we learned in 10.1, and I can tell that because the two sides don't meet, that limit does not exist. But let's continue with what it says. Because as x approaches 0 from the right, the y values, so if I jump on this graph and I start heading towards x equals 0 from the right side of the graph, I can tell that the y values go to 0. But as x approaches 0 from the left, so if I come in from the left side of this graph towards where x equals 0, I can tell the y values go to -4. Okay, so that gives us a different kind of a limit notation. We can say that the limit as x approaches 0 from the right of this function. And so if you put like a little plus sign, kind of like an exponent, right, as a superscript, that means from the right. So the limit as x approaches 0 from the right. So the two sides don't have to meet. You only look at the right side. In this case, we would say that that's 0. But the limit as x approaches 0 from the left, so you use a little minus sign from the left, so the y values from the left go to -4. And it's because those two numbers are not the same, it's because of that the overall limit as x approaches 0 of this function does not exist, right? Because the left doesn't equal the right. Okay. So look at my next example. It says, sketch the graph of the piecewise function. So first we're going to draw this graph, and then we're going to answer these next two limit type questions. Well, all right, so I have two pieces. So on the right side, I'm sorry, let me back up. On the left side of 0, okay, you going to erase or what? There we go. Okay, so we were talking about graphing this this piecewise function. So if x is less than 0, okay, so we're talking about the left side of 0, I have the graph 1 over x squared. Well, you may or may not remember, the graph of 1 over x squared it's kind of like the 1 over x graph that has both pieces on top. But since I only want the part when x is less than 0, that means I don't want this piece over here on the right. I only want that piece on the left. Okay, so that's going to be the one side, and then on the other side of 0, I want the line x plus 1. Well, that's y-intercept of 1 and a slope of 1, so up 1 over 1. If I were to draw the entire line, it would be this piece, right? But I only want the part when x is greater than 0, so I only want from here over this direction. I don't want this side. Okay, so there's my piecewise function. And if I look at the question down below, it says, find the limit as x approaches 0 from the left. Well, as I come in from the left of this function, so I'm coming in from this direction, I know I'm going towards, because of the graph 1 over x squared, aren't the y values shooting up to infinity? So I could say this equals infinity. Now, even though I know it's going towards a vertical asymptote, I don't have to say does not exist. I could say does not exist. But by saying infinity, you're giving a more specific answer. You're saying the limit does not exist, and the reason it does not exist is because the y values go to infinity. Okay? So don't mistake infinity for meaning somehow that the limit exists. And then look at the next part. It says, the limit as x approaches 0 from the right. Well, if I come in on this graph towards 0 coming from the right side, it looks like the y values are going towards 1. Okay, so I looked at two separate sides. Now, look at this one. It says find the limit as x approaches 2 from the left. Well, if I don't have a graph, at first I don't have to worry about left and right, because if the overall limit exists, if there's a y value, then left and right are the same thing. So treat left and right just like you treat all of the other limits until you get to a point where you're like, okay, this is undefined, I don't know what to do, and I have to look at a graph. Well, let's treat this as if it were just a regular old limit. First thing I would try and do is substitute. I can't because I get 0 over 0. Then I might try to factor, which I think I can factor this. And once I get the denominator factored, I think you'll notice that those factors will cancel. It's going to leave a -1. So actually, I'm finding the limit as x approaches 2 from the left of -1 over x plus 2. Okay, can I substitute? Now make sure you notice when I say from the left, I'm not saying -2. I'm saying +2. I'm just coming from the left of +2. All right, so just plug in a 2. If I plug in a +2, I'm going to get -1 over 4. So in this case, because it actually came out to be a value, I didn't have to worry about left or right. This could have been left, it could have been right, or it could have just been the limit as x approaches 2. Okay, so look at the next page. I've got several that look very similar. In fact, you'll notice on number 2, 3, and 4, all of those are using the exact same function, 3 plus x over x squared minus 9. So we'll look at that in a minute. Look at number 1. This one's just a little bit different. It says, find the limit as x approaches 3 from the left. Okay, I don't care about left or right to get started. I'm just going to see if there's a y value. So if I substitute, oh, nope, it's 0 over 0, but that's fine. I'll do like I did a minute ago. I'll factor and see what's going to cancel. So hopefully, just like that last one, you can tell, hey, look, those cancel. It leaves a -1. So now if I substitute in my 3, I'm going to get -1 over 6. And in this case, it didn't matter. Okay, great. Set that aside. Look at number 2, 3, and 4. So they all have the same function. Notice the difference here is that the first one says from the left, the next one says from the right, and the last one just says x approaches 3. All right, so I start off trying to substitute. If I get an answer, like if I can substitute and factor and get an answer like I did on number 1, then all of these, 2, 3, and 4, are going to have the same answer. So let's see what happens. So start by factoring, which is going to be similar. X plus 3, x minus 3. Okay, I still have something that cancels, just leaves a +1 this time. So can I substitute? No, if I substitute, I'm going to get 1 over 0. Okay, that's undefined. So I know this limit doesn't exist, but let's think about it. Because the function that I'm looking at here is 1 over x minus 3, think about that graph. Isn't that just the 1 over x graph that's moved 3 units to the right? So isn't this just the 1 over x graph over here? So I can tell by looking at the graph. Let's actually answer the question. They said, what's the limit as I approach from the left? Well, as I go towards 3 from the left side, aren't the y values going to -infinity? But if I go towards 3, notice this time it says from the right side. So if I'm coming towards 3 from the right side of this graph, aren't the y values going to +infinity? And again, don't confuse this. Neither of those limits exist. I could just as easily have said does not exist, right? Does, well, I forgot my D. Does not exist. It's just that saying that your answer is +infinity or -infinity is a more specific answer than does not exist, right? The reason it doesn't exist is because it goes to +infinity or -infinity. But look at number 4, same graph, but it doesn't say left or right. So in this case, I can't say +infinity because that's only one side, and I can't say -infinity because that's only one side. So all I can say on this one is does not exist. Okay, so the second concept in this section is continuity. So the root word continuous. And if I just said, hey, draw a graph that's continuous, without even thinking about it, you would kind of go back to what you know the word continuous means. You would just kind of draw a graph that doesn't have any breaks or holes. It's just a nice smooth curve. Okay, well, intuitively, that's what continuous means. So intuitively, continuity means that you can trace a function without picking up your pencil, right? In other words, the graph cannot have any holes or breaks in the graph. Now, there are different ways to have breaks, but one of the ways to have a break in the graph is to have a vertical asymptote. This is probably one of the more common kinds of breaks in a graph. Okay, so like if I look at this first graph, I can look at that and tell there's a hole at -1. So that means this graph is not continuous at x equals -1. It seems like it's continuous everywhere else except at -1. Or I can look at the second graph. I can say, hey, because there's a break in the graph at 0, this one is not continuous at x equals 0. And the last one, similar to the first one, I can say, hey, there's a hole. Even though there's the point up above, that's okay. There's still a hole in this graph at x equals 5. So I'm going to say this one is not continuous at x equals 5. Okay? I mean, that's what, it's easy to look at a graph and say, oh, yep, it's continuous, or no, it's not continuous somewhere in particular. What gets a little bit more tricky is giving the reason why. And I know it's easy for us to say, oh, there's a hole, or oh, there's a break. But those aren't mathematical reasons. Okay, a hole is not the math definition, or a break in the graph is not the math definition. So here's kind of the formal definition. Mathematically, there are 3 conditions that must be met for continuity to exist. Okay, so first of all, we're going to say f of c has to exist. Well, remember, the notation f of c means the specific point. So in other words, the actual specific point has to exist. Okay, the point exists. So when I look at that first graph, there is no point at x equals -1. Remember, if I'm looking at this on a calculator, I wouldn't even see that circle. I would just see kind of a space in the graph. So what that means is f of -1, right, doesn't exist, or is undefined, however you want to say it. I'll just say does not exist because that's what we have down below, right? F of -1 doesn't exist. There's not a point there. Now, if I look at the second graph, there is a point. So on the first graph, I can say it's not continuous, and the reason is because f of -1 doesn't exist. But on the second graph, yeah, I can tell it's not continuous, but it's not because f of 0 doesn't exist, because f of 0 does exist. Look right here. F of 0 is 4. Okay, so that's not the reason that the second graph is not continuous. If I look at the third graph, the same thing. Yeah, I know it's not continuous, but there is a point at f of 5. In fact, I can tell f of 5 equals 3. So yeah, it's not continuous, but the reason is not because the point doesn't exist. The point does exist. Okay, so what's the second condition? Well, the second condition is that the limit there has to exist. And when we say the limit exists, we're saying that the left side of the graph equals the right side. So when I look at the first graph here, I can look at that graph. I can tell the limit exists, right? Because as you go from the left and the right, you get a limit. So yes, I know that the limit as x approaches -1 of this function, and actually I can say, hey, the limit equals -3, but it doesn't matter. I don't even really care if the limit exists on that one, because I already know the reason it's not continuous. The reason that one wasn't continuous was because f of -1 doesn't exist. Okay, look at the second graph. All right, there it is. The reason this one's not continuous is because the limit as x approaches 0 doesn't exist. The limit as x approaches 0 of this function doesn't exist. That's why the second one's not continuous. And on the third one, does the limit exist? Yeah, it does. The limit as x approaches 5 of this function equals 1. So we've already said why the first two don't exist. The first one was because f of -1 didn't exist. The second one was because the limit didn't exist. But on the third one, f of 5 exists and the limit at 5 exists. So look at the third condition down here. Number 3, the limit has to equal the point. So in other words, at the place where the left side and the right side come together, the actual point has to fill in that spot. That's what makes a function be continuous. So look up here at the third graph. Definitely we know it's not continuous. F of 5 exists, the limit at 5 exists, but they don't equal the same thing, right? If they equaled the same thing, that point would be dropped right down in there and it would fill in that hole. So the reason this one is not continuous is because the limit as x approaches 5 of this function does not equal f of 5. I mean, I can tell because we said f of 5 is 3, but the limit is 1. They obviously are not equal. Okay? So, example number 1, find all discontinuities. Okay. Well, remember, what does it mean to have a discontinuity? It means you might have a hole or you might have a break, which is probably, if there's a break, it's probably a vertical asymptote. So we need to channel our inner first semester. Let's see, holes and vertical asymptotes. Remember, vertical asymptotes are when the denominator is 0. Holes are when the factors cancel. So we need to put this in factored form. Let's see, 3x and 2x. How about we go with 4 and 3, minus and plus. Is that going to give me a negative x in the middle? I think that works. And then in the denominator, we're going to have 2x plus 3, 2x minus 3. So you can tell these factors cancel. So we know there's a hole at x equals 3 halves, right? Because that's what made that factor equal 0. And we know there's going to be a vertical asymptote when this other factor equals 0. So when x equals negative 3 halves. So the question was, find all discontinuities. All right, both of these are discontinuities. Discontinuities. Both of those are discontinuities, places where you have holes or breaks in the graph. However, we're going to say that one of them is removable, because remember, a removable discontinuity is one that is a hole. So this one at 3 halves, we would say is removable. So if it's such that, look at the first graph, if it's such that the limit exists, but there's just a hole in the graph, that's called a removable discontinuity. I could have just as easily have said the third graph because it was just a hole, and yet the limit existed, it was just a removable discontinuity. Again, just words. Look at example 2 over here. Find the values of a and b such that f of x is continuous. Okay. So I have a piecewise function, right? So assuming each piece by itself is continuous, then what would make this overall be continuous is if all 3 pieces met up. Now, think about this. So there are 3 pieces to this graph. Here is negative 1. Here is 3. Okay. So one piece of this graph, the first piece, exists on the left side of negative 1. So that first piece is over here somewhere, right? Now I know I could draw it, but I just want to think generically for a minute, all right? And then the second piece, whatever that graph looks like, exists between negative 1 and 3. So it exists between here all the way over to 3. So whatever that graph looks like, I don't know, but it's in that section. And then the third piece exists on the other side of 3. So from here, on out. So there are 3 pieces to this graph. Now, on this particular one, I happen to know what they look like. I happen to know that that green piece is just a horizontal line at 2. Okay, so it's just coming in here. It's a horizontal line at 2. And I happen to know that that red piece is just a horizontal line down here at negative 2. But whether I knew it or I didn't know it, the middle piece, I know it's ax plus b. Actually, I do know that's the form of a line because it kind of looks like mx plus b. But let's pretend like we didn't know it was a line. Let's just pretend like we have no idea what it looks like. It's just some piece in here in the middle, I don't know, for all I know it goes up and down, I don't know. But in order for this to be continuous, I need, when this one comes right here, I need it to meet up with that graph. And when I head over here, I need it to meet up with that graph. If they meet up, then this overall is a continuous function. Okay, so what I'm really concerned about is what's happening right here when x equals -1 and what's happening right here when x equals 3. Okay, so when x equals -1, I need the green and blue piece to have the same y value. That would make it be continuous. And when x equals 3, I need the blue and the red one to have the same y value. Okay, well let's go up here. Let's look at it. For the green piece, what is the y value when x equals -1? Well, it's a horizontal line at 2, so the y value is 2. What about for the blue piece? What is the y value when x equals -1? Well, if you plug in a -1 for x into the equation, you're going to have a times -1, so -a plus b. So if I want those y values to be the same, then I'm saying I need -a plus b to equal 2. That is going to force these two pieces to come together. Okay. Unfortunately, that doesn't tell me what a and b is. I still have lots of possibilities, right? Why? Because there's two unknowns and only one equation, right? Well, what's going to force these two pieces, the blue and the red, to come together? Well, if the y value at 3 is the same. All right, great. What's the y value? What's the y value of the middle piece at 3? Well, plug in a 3 for x, and you're going to get 3a plus b. And what's the y value of the red piece when x equals 3? Again, it's a horizontal line at -2, so the y value is -2. So if 3a plus b equals -2, then that means the blue and the red piece coming together, and overall we're continuous. Well, how am I supposed to know what a and b is? Solve the system. I have two equations, two unknowns. I should be able to solve, right? Okay, so let's see. How about if I take this first equation and solve for b, right? Add a. So b is going to be a plus 2. So come over here. I'm going to put this a plus 2 in place of b. So 3a plus a plus 2. So I've got 4a equals -4, and that means a has to equal -1. But how am I supposed to know b? Oh, glad you asked, right? Plug a -1 in for a, and so b is going to equal +1. So if that middle piece had been the function -x plus 1, if that middle piece had been this line, these two would have connected. And you can kind of picture that. Let me just draw in the line that connects those. If I draw a line that connects those, does it look like that could be the graph of the line -x plus 1? Yeah, it does. Now, like I was saying earlier, I'm not saying you couldn't have solved this specific problem without doing a system. I believe that, but because of the line. I'm saying I'm trying to show you how to do this if you don't know what kind of graphs they are. Maybe they're not lines. Maybe you have a parabola connecting to a cubic, connecting to a rational function of some type. Okay, so this method will always work in order to force something to be continuous. All right, so that was section 10.3.